Hello and welcome to PEEPanEIP, a podcast where we deep dive into the latest development and proposals in the Ethereum ecosystem. I'm your host Pooja Ranjan, and today we have a fascinating episode lined up for you. In the next few minutes, we would be exploring EIP-2537, a proposal that introduces a precompiled BLS-12-381 curve operation. This EIP has significant implications for the efficiency and security of cryptographic operations of the Ethereum blockchain. Documented in February 2020 and moving from draft to review, this proposal was in stagnant status for quite some time. Back to the review status, this proposal has been through many discussions to be included in the Ethereum mainnet upgrade. But what exactly is EIP-2537? What are BLS-12-381 curve operations? And why are they so important? To help us unravel these questions, we have an expert guest with us. Alex Stokes, an Ethereum developer and co-developer meeting facilitator, who is also one of the co-authors for this proposal, is here to break down the technical details, discuss the journey of this EIP, and explain how it aims to enhance the Ethereum network. Welcome back to our show, Alex.
Yep, thanks for having me.
For people just joining with the PEEPanEIP family, Alex Stokes organizes MEV community meeting and has authored multiple EIPs for the Ethereum ecosystem. He has been generously taking out time to explain them. So please check out links in the description for his earlier talks on different proposals, including EIP-4788, EIP-44s, EIP-4895, MEV Boost, Altair, and so on and so forth. Getting back to today's talk, Alex, let's start with a small introduction. I like to call it Meet Your Core Dev section. So can you maybe tell our listeners about your professional background and the journey with the Ethereum blockchain development?
Sure, yeah. So I do research at the Ethereum Foundation, and I've been doing that for, quite a while now. Yeah, I guess my sort of overarching story is maybe a little funny, maybe not, but I also think similar to a lot of people who find their way into this space. So before I was really doing like sort of, full-time core development research and things like this, I was just a fan. I heard about Ethereum a long time ago and thought it sounded super cool, the original vision of the world computer and all this. So that got me like intellectually interested. And then, yeah, basically I started just with like open source contributions. Yeah, many years ago, we had sort of this vision of ETH2 that would be like a serious overhaul to the protocol. And so I started working on some things there because, again, many, many years ago, we were even thinking about having the proof of stake component of Ethereum today actually be facilitated via smart contracts on the proof work chain that we used to have. And yeah, like one of my earliest sort of concrete open source contributions was essentially this piece to verify statefulness of validator validations. That's a mouthful, so let's phrase it differently. Essentially, the validators would be able to point to smart contract code themselves that would validate their signatures on chain, sort of like an early account abstraction, but for proof of stake validators. And so that's not how it works today. That idea kind of ultimately was scrapped, but at the time it was, at least some like interesting research that we were investigating. And I wrote sort of this smart contract that would then verify these other smart contracts validators wanted to use, because again, for reasons of having the chain be deterministic and all this, if I can use anything as my signature as a validator, I also wanted to be deterministic. And so there's certain things within EVM that a validator couldn't do, but otherwise they would have full flexibility of EVM to say, this is my signature as a validator, to I've signed off on, say, some attestation, this is how you should process it. Yeah. So anyway, fast forward to today, and we have the latest and greatest Ethereum. And it definitely keeps me busy.
Of course, and the contribution when it comes to the Chapela upgrade, that was awesome. For withdrawal, that was quite significant as well. Very well, with the introduction out of the way, let's peep into EIP 2537.
Right. So today we're talking about EIP 2537. I believe this title is directly copying EIP, which is precompile for BLS-12-381 curve operations. So what does that mean? I think the first thing to recognize with the EIP is it has a very long history. which I mentioned, it was created in February of 2020. And yeah, it's been many years now. And like, I think as we'll see, like there are important use cases that this functionality unlocks, but it's always kind of been this thing where, there's only so much bandwidth, let's say, for every protocol upgrade. And so then, you have to prioritize what are the most important things. And well, I'll touch on this a little bit later, but I think when we first had this EIP, people were less comfortable with the software implementations and security implications and all this. And so that, again, just coupled with other hard forks having sort of more flagship features, let's say, it's taken a while to bring this one to the forefront. However, that being said, it has been included in Pectra, which is the next hard fork we have. So that's very exciting. And I think everyone, not just me, many people have contributed to this EIP at this point. And yeah, everyone's very excited to see this. I was also looking, one of the earliest PEEPanEIP episodes was actually on this EIP. I think it was episode 3. So it just gives you a sense for, how long this has been out in the core development process. And I thought it'd be interesting just to like kind of sort of take a diff between that presentation and kind of where we're at today. So I actually just grabbed the slides. Other episode was by Alex Stokes, who was involved very early on with the CIP. There's a link here to the slides. The next couple of slides have this like blue background. Those are just from his presentation. And then we'll kind of recap at the end with like how some things have changed and bring us up until today. What does this EIP do? So in particular, it adds precompiles for this very particular elliptic curve. And I'm not sure how much cryptography background people have in the audience, whoever's watching this, but essentially there's like a set of mathematics that we've learned that we can use to support these different cryptographic schemes that we want. For example, like signature schemes, right? So in particular, with this curve, this is the curve we use at the consensus layer. That's like probably its biggest sort of motivating factor at this point is just that with respect to validators in proof of stake system, whenever they sign off on anything, they're using this particular elliptic curve, right? And so what that means is that there's like sort of a spec of some math, and what you can do is build on top of this sort of framework to get secure cryptographic constructions. Again, for example, BLS signatures. Already off the bat, there's like an interesting name collision here. So if you get into this stuff, you'll see like BLS many places. There's actually 2 schemes already. So there's BLS-12-381. This is a particular elliptic curve. There's also the BLS signature scheme. And I forget exactly how it is, but basically between the B, the L, and the S, these are the initials of 3 people. There's actually 4 people because with the curve, there's a set of 3. With the signature scheme, there's 2 of them are the same. I think the B and the L are the same, and then there's a different S, something like this. So either way, that's just something to keep in mind. And this is what different Alex called out in the last talk. So that all being said, we do use this curve at the consensus layer. We also, in fact, use this signature scheme at the consensus layer. One really cool thing that the BLS signature scheme supports is aggregation. And this is how we actually unlock a huge validator set, right? So there's over 1 million validators in Ethereum today. And the way that we make this performant is that rather than have to verify, say, like 1 million signatures, per block per unit time, you can actually aggregate them into a much smaller number. And that's a cool thing that the signature scheme supports. And it turns out that this curve is compatible with the signature scheme. That all being said, it is like a pretty new and modern curve. This is also probably why it's not, there's like, you may ask why is it not already in the protocol? Well, it turns out it's actually like a pretty new curve. That being said, cryptocurrencies other than Ethereum across the whole industry have kind of settled on this curve. It has, nice features that we want, good security level, and things like this. So in particular, the other Alex called out, right, this elliptic curve, it supports pairings. This again refers to some mathematical operation that gives you these nice cryptographic features. So like in particular, the aggregation I was talking about, so you need pairings to do this. It's a performant curve, so that's nice, just meaning when you actually implement the thing, it's like very fast, at least fast enough for our purposes. And it gives you the security parameters that we want. Like in particular, it's 120 bits. One interesting thing here is there actually is another elliptic curve. There's another set of precompiles for this other elliptic curve in Ethereum, the Ethereum protocol already. It's this BN254 curve. If you go to use snarks on Ethereum today and you actually want to verify the snark proofs on chain, this is the curve that you're using because this is literally the only one we have. I guess some other helpful context is that you could imagine, okay, why don't I just like write the curve that I want, native EVM, I could just write a smart contract. And this is possible, but it turns out that due to the complicated nature of these curves and the cryptographic schemes on top of them, this becomes very expensive very quickly, for example, in terms of gas. And so this is why then we need precompiles. And again, to sort of round out the context here, precompile is something that gives you sort of like a shortcut to do these like very sophisticated operations. So rather than say, pay all the gas it would require to like do these, elliptic curve pairings or these different operations we'll see later in the talk, you basically sort of like get a discount because you can escape the EVM, go to a native implementation, and saves you a bunch of gas. So this is the curve, and the EIP gives us these operations of the curve. The way this is kind of structured is that the curve is just a mathematical construction. You then want to do different operations, sort of, like mathematical operations, like you might be familiar with like addition or multiplication, say from grade school. It's like a very analogous concept here. And then the cryptography is built up using these, additions and multiplications and various operations to implement the schemes that we care about. Again, for example, like BLS signatures. So just to round out the slide here, at the bottom here, it says like this 254 curve only has 80 bits of security. This is actually a big selling point for this EIP, is that the curve that we have on chain right now actually has had some attacks in recent years that suggest it has a much lower security sort of parameterization or threshold than we initially thought. So it's fine enough, but it definitely motivates getting this new, more modern curve into the protocol. Right. So what does this EIP actually do? Well, it gives you these different arithmetic operations. Okay, so what does this EIP actually do? So it gives you these arithmetic operations like I was just talking about. So the way it sort of works is that you have the curve, you pick a subset of points on the curve, which forms a algebraic group. You can then do additions in this group. You can do scalar multiplications, which, basically just many additions together. And these are like sort of the very primitives that you would use in all these cryptography schemes. There's another special thing called the pairing. This is a much more sophisticated operation, but it's, again, very important for all of the cool cryptographic properties. Again, for example, like aggregation that we would care about. You do also have this last bucket, map to curve. So this is actually not strictly related to the BLS-12 381 curve, but there are other things that you need to, again, for example, verify BLS signatures. So this is kind of like zooming out a bit, and this EIP really is not just the curve. It does have the curve, and there are applications that just need the curve, for example, ZK snarks over the curve. But there's other things you would want as well for like BLS signatures. And again, like a huge use case here is actually just going to be verifying signatures of validators from the consensus layer inside the EVM. So then we need these other operations. They're called map to curve. Dig into more of this if you'd like to learn more, but ultimately they're also there. I will call it a resource while we're here. So if you are interested in learning more about this stuff, Ben Edgington has a really great article. He was working on a ticket client for quite a while. I think he's now at Optimism. That all being said, he has a really great explainer on the curve and sort of how all those pieces fit together, I think in like a really nice, readable way. So shout out there. Okay, so that's kind of why, like what the EIP kind of is and like what it gets us. The question now is like, why do we care? So a big one here is like people using ZK snarks. And essentially, it's just like a very nice curve for them. I think we'll touch on this a little bit later. I think some of the sort of snark meta has changed just because the technology has evolved since, say, 2020. People think about this a little bit differently now, but especially at the time when these slides were made, say a few years ago, you would use this curve to make very nice snarks that would still be performant while, for example, being higher security and more performant, or it says capacity here. So basically just letting you make more complicated statements for your snarks. Again, the next big use case here is BLS signatures. So anything that touches the consensus layer is going to have a BLS signature. So you can imagine all the different schemes people think about, like restaking, rollups. You could imagine like sequencers of some rollup are using BLS signatures, any sort of like cross-chain interaction. I think this was like, again, more in the meta a few years ago, but you could imagine that like we want to bridge Ethereum to like Filecoin. That's the example here. Maybe a little more modern example would be like bridging Ethereum to like, I don't know, Celestia or something like this. But essentially, to the extent that Ethereum uses these signatures, if you want to be aware of some of their chain's consensus, you would then want to verify BLS signatures of their chain. And you kind of need this EIP to do this. There's no other way, again, to do this natively in EVM. And so that's what motivates the precompiles and in turn this EIP. Random speak-ins, so there's a huge body of cryptographic work around this concept, which is basically just like having a source of actual like a random number is one way to think about it. and then have it be, again, trust minimized so that there's no central party controlling it. And, how do you actually go about building this? Again, I think I'm not a cryptographer. My understanding is that the cryptography maybe has moved in a few different directions, but ultimately this BLS-12 curve would be like a good candidate for many of these types of randomness constructions. And there's like cooler stuff on the horizon. Vector commitments, that's a particular cryptographic construction. If you think about it, it's actually kind of how we end up, well, let me put this differently. So the way that we have blobs on Ethereum, there was not quite the concept of blob when these slides were made, but now today, if you come to Ethereum, you see we have blobs. This is the way we're going to scale rollups so that we can scale Ethereum overall to presumably the entire world. And it turns out that we actually end up essentially using this curve and the blob commitment's there. And you can kind of think of that as a vector commitment as well. So it's cool to see like calling out the bleeding edge R&D here is now actually on mainnet today. This next one, witness compression, what this is referring to is essentially, if I want to make a proof of some statement, essentially like imagine like there's some fact in the protocol, like there was a block at this height, or like, maybe to make it more concrete, let's say there was like some state change. And I'm teeing this up to Merkle if you're familiar with that. And so basically what this is saying is that if we go to like a stateless Ethereum, rather than have the state locally, you in turn instead just have a proof of the state. And then as a local node, when I verify the stateless block, I don't need to actually have the state because I essentially just have a proof that the state is what someone claimed it was. And there's many benefits to this. I don't know if there's been like a Verkle PEEPanEIP, but there will be soon. It's one of the big R&D projects coming in the pipeline. And this all being said is, you can imagine using this BLS-12 curve, do what here is called witness compression. So when you have these state proofs, they can actually be quite big. You can imagine making the proofs and then sort of compressing them all into a snark over this curve. So again, very much leading edge, but super cool applications of cryptography to make Ethereum better. And I think this was the last slide from the earlier presentation. So yeah, this was kind of looking at what's done. And you can see some of it's kind of aged already. Like for example, no one really talks about open Ethereum anymore. We've kind of moved away from this ETH 1.0, ETH 2.0 nomenclature. But all being said, yeah, there's a large number of limitations at this point. Different clients. Well, I think at this point, most clients have settled on one implementation, this BLST library, at least in production. And that all being said, it's now been at the consensus layer for many years. People are used to having it in production, having it in like their clients, their building, their tooling, their testing pipelines. And this is actually part of kind of what's taken this EIP so long to get to like a point of inclusion, is just gaining confidence with this actual implementation. Because as you might have kind of understood, the cryptography itself is like quite complicated, and like the very low level details of like this curve and this, there's like all of this algebraic geometry to like implement pairings, and it gets really complicated really fast. And so there's actually some pushback, say even in like 2020, 2021, was that we didn't essentially understand the libraries well enough to put them into clients. That certainly has now changed, where people now feel more comfortable, and that I think unlocked a lot of sort of, again, yeah, these sticking points around including this EIP for a mainnet hard fork. So those were slides from the previous PEEPanEIP on this EIP. Again, I just copied and pasted them here. And now we can kind of zoom out and say, okay, like, yeah, where it's been maybe like 4 years, like what's changed since? And the big one, I think, is what I was just talking about, where we now have sort of, again, as core developers, we have a lot of comfort with the library implementations of this curve that we have. They've been on mainnet, they secure Ethereum, people feel very comfortable with them, and so this is very good. A more minor thing, but important, is that we've updated the gas cost since like the initial draft or creation of this EIP, and that's just reflecting the fact that, people have libraries that are more optimized, or we understand just better how they fit in like the gas schedule of other things in BVM. And so that's very normal, just to like have the gas cost be updated to reflect benchmarks on modern hardware and things like that. Another thing that has changed in, say, like the last 6 months is we now mandate subgroup checks. And again, this is sort of like a cryptographic detail that I won't really get into too much, but basically, when you go to actually use these curves, you need to make sure that you are using points sort of in the actual specification of the curve. Otherwise, you can provide data or inputs to these precompiles that look right, but they basically would give you, let's say, the wrong answers or like bad answers. And we kind of went back and forth on this. It's kind of a question of like user safety versus the cost here. And what I mean by that is you can imagine that we don't have these subgroup checks, and that just means that like you have to do them before using the precompiles. And so that means is like as a user, you have to do them yourself. So this is fine. It would actually make the precompiles cheaper, but the trade-off here is like it's going to be probably more expensive for you as a user if you have to do them yourself. So instead, you can imagine the precompile doing them, they kind of get ruled into subsidizing the gas cost of the whole operation. Right. Actually, okay. So I think I misspoke. So essentially, the trade-off here is between user safety of having the precompile do it for you versus the precompile being more expensive. And there was some research here into like doing this because like generally I think we all want to lean the direction of user safety. That sounds like a great thing. These things are already hard enough to use, so we like to take off the various spoke guns where we can. One notable exception is with like point additions. And again, this was very much a cost thing where given like even modern day subgroup checks for these different operations over this curve, the ones for addition were too expensive actually. And so then again, it was decided to omit them for additions, although we do have them for the other operations. Another thing that's like more interesting, just to see this play out in the context of everything, is I would say like essentially the way people think about making snarks has like changed quite a bit simply because of all the development and progress in that field. And what this means is that like when you talk to people about state of the art like snarks, they would actually maybe even look at different curves or different operations. That doesn't mean that you couldn't use this curve for snarks or like useful things. But yeah, just I think kind of changes the context a bit, which is just interesting to see how that changes over the years. Another thing is like more progress on actually a stateless Ethereum. So I think that's a big use case of this curve is essentially making snarks of like state proofs. And Verkle itself is using a different curve. It sort of looks like BLS-12-381, but it's a different curve essentially for performance. Because the whole thing there is like if we are in a stateless Ethereum, you'll have like proofs of like the state change in every block. These can be quite big. And moreover, they're going to take time to generate whoever's making the block, right? And so there you want to pick basically the most efficient curve that is still secure for this use case. And my understanding is that essentially, even though there's a different curve for Verkle, you could still actually then form a snark over this BLS-12 curve. And so then you could like do things like verify state proofs inside the EVM, which would unlock a lot of really cool applications. And the newest super cool thing is actually it's finally been scheduled for inclusion in Pectra. Again, this has been an EIP people have been working on for many years in all sorts of different capacities. And yeah, it's really exciting to finally see it at a place where it will actually go into the mainnet protocol. Yeah, so those are all the slides I had. Yeah, are there any questions?
Thank you. This was an awesome presentation. It was a great idea to include some of the content from the last presentation on this topic. You talked about what is the CIP, what changed since then. I think the content that you have added over here are valuable and our listeners would find it very useful. For anyone who missed EIP-2537 earlier talk, it was an active discussion and was also being considered for the upgrade at the time when proposed in 2020. As Alex mentioned in the presentation, it's worth checking the recording of the overview of this proposal on PEEPanEIP. Yes, indeed, it was episode 3, EIP-2537 in 5 slides with Alex Stokes. So from episode 3 to this episode, which is episode 133, we have been added by 130 proposals. I'm sure the series is helping people to get the knowledge. And from Alex Vlasov to Alex Stokes, this proposal has also moved from upgrade under consideration and now being included for the Pectra, which is the next upgrade. So congratulations to the team who has been tirelessly working behind this proposal. And yes, anyone on the call, if you guys have any question, please feel free to drop it in the chat and I'll be happy to invite you to take that question. But for Alex Stokes, I have a few more questions, though you have tried to explain the proposal in such a way that it has covered most of the basic questions. Since the initial proposal, what would you say as the major change to the specification And you talked about trade-off of security versus expensive. Why was that change necessary and how that has improved this proposal now?
Right. So, I mean, the first thing off the bat is just that it makes it more secure for people to use. So again, this cryptography is like very low level, and like, to do it well, you kind of actually need to all this context around like both like very advanced mathematics, but then also like have all the software knowledge of like how these things actually go and work with the libraries and how they're actually used. And if you look at the field of cryptography, like this is actually like a running theme throughout like the whole history of the field, where a cryptographer or a set of cryptographers will have like an idea for like a really cool cryptographic feature or some sort of construction. And then it's sort of this like difference between theory and practice, where like you then have to take the theory and you actually have to implement it and then put it out in the real world. And there have been many cases, again, all over time where you get like subtleties implementation that are quite, not quite right, or it's like maybe it's like correct, but it's like hard to use. And if you don't use it exactly in the right way, it turns out you can actually, in some cases, completely make the scheme insecure. So this is like a running theme throughout applied cryptography broadly. And essentially for Ethereum, like we want it to be as secure as possible in like all senses of the word. And so definitely where it makes sense, yeah, we should definitely prefer things like user safety in terms of like removing these bookends. Where would it not make sense? Well, and again, we already see with the EIP, like there could be cases where it might just be so expensive and like the actual sort of, again, I keep using the phrase foot gun, but you can imagine that like it's not quite that disastrous, at least given the cost. So yeah, that was kind of the thought process there. And between everyone working on the CIP, like I think we feel like we're in a good place.
Definitely, it is always good to be safe than sorry, and I have seen many proposals being deferred to get included in the upgrade if we are not 100% confident about its security. So, today we are at a place where EIP 2537 is being accepted for the upgrade Pectra. I would be curious to hear your thoughts and anything that you have to share with us about the challenges or the obstacles that was faced during the process of inclusion in the Ethereum network upgrade. What changed since 2020 to 2024 that it is being included in Pectra upgrade?
Yeah, that's a good question. And I think it does kind of highlight both like the core development process broadly, and then also just in particular, yeah, like what it actually takes to get something to mainnet. So this is actually, I think, a really nice EIP, simply in terms of like, it's like a case study almost of like core development broadly and like how we think about changing the Ethereum protocol, which I think most people would agree is like very important and very valuable. And so, yeah, what that means is you can't like sort of move fast and break things. We need to carefully consider every proposal and make sure, it's been vetted many, many times over before we actually think about changing the protocol in any particular way. And with this one in particular, it's had a long history. When it first came out, I mean, this was the initial sort of pushback, was it's like, okay, well, as core developers, we know the client software very well, we know the protocol very well. We might not necessarily have the cryptography expertise. And with these sorts of EIPs, these ones that are adding these precompiles for cryptographic operations, it's kind of like I was saying a minute ago, where you do actually like to do it well, you do also need to like essentially have, a PhD in math, PhD in like software engineering. Like you need a lot of like context to know where you might go wrong and avoid that. And so that was the initial pushback, was like, well, like, yes, this is important. We see it being used in the consensus layer, for example. So it's obviously like a valuable thing for Ethereum. That being said, as core developers, like we might not feel that we have the expertise. For example, if something goes wrong, there's a bug implementation, like we don't have the skill sets sort of on call 24/7 to like immediately diagnose the bug and like resolve something and like ship an update. Like that would be the sort of disaster scenario, is like I mentioned this BLS-2 library people are using. Like if there's a bug in this library, like we would go to the authors and maintainers of that library and they would fix it. But what if they weren't available at some particular time? And so then because of that, I think many client developers were uncomfortable initially, given the like sort of relative immaturity of the library. And these things just take time to resolve. And that's what we've seen is, as we've been using these libraries on mainnet and the beacon chain and all these different places, and they sort of prove their sort of robustness over time, people get more comfortable. And then you get to a place where it's like, okay, I feel a lot more comfortable using these things in mainnet, for example, in this set of precompiles. A big help is like we do actually end up using like the same library and again, the same collection of cryptographic, let's say, operations with the blobs. And so like, it's not exposed in the same way, but you end up already having this code in the clients. And so, yeah, if anything, that just unblocks this sort of sticking point with respect to including this EIP. And yeah, so here we are. It's taken a while, but I think we've gotten to a place where people are comfortable. And maybe just to end on this point, like I do really think this is a nice case study for like core development broadly, because like I guess the point I want to get across here is that like it can actually take a very long time to change the protocol in some way, even when everyone agrees, yes, this is a very important change, this is very useful, it's going to like really improve the state of things. Like it can still just take years even of people just like hammering on it, like pushing it through the all core devs process. Like, yeah, it goes to really point out how, let's say, tricky like the like core development process can be. That being said, it's like one of, I would say, Ethereum's greatest strengths is like you do actually want it to be hard because it is such an important thing to go and change this protocol that so many people rely on.
Absolutely. The other day, I was having a chat with Matt Gannett, and he did mention forcing core developer is not something that people can do. They cannot influence just to include their proposal unless they are ready. They are not ready. So we need to bring the proposal at a place where most of the core development team are comfortable feeling getting it included in the upgrade. Glad we are there yet. Talking about this inclusion, I would be curious to hear more about some real life use cases for this EIP. If you have any suggestions for application enthusiasts, like where this proposal can be used.
Sure. So I do think that like snarks are a big one. So if you have any sort of cryptographic applications where you want zero knowledge proofs, like this is going to provide you with a curve that is more secure and hopefully more easy to use than like what we have today, which is this other BN254 curve that I mentioned. So that's a big one. People want to do things like there are many sorts of like client like constructions. Essentially, like if I want to verify consensus of some other chain or even Ethereum itself inside the EVM, then you would want access to this curve to be able to do it efficiently. So that's really nice. And what else? So I think that like the Berkeley use case is really interesting because we'll be able to like have really efficient state proofs in the chain, like within the EVM. And yeah, I mean, I think it's kind of TBD what this unlocks, but you could imagine all sorts of applications that like want to do something, you know, based on some state change. And like right now, it might be really hard to actually prove that some state changed. Once we have Merkle and kind of tee everything up, it'll actually make these applications much more feasible than today. Let's see what else. I feel like there is one other thing that I just had in mind, which was, yeah, I mean, maybe just to give like a concrete example, like you could imagine that there's like different staking pool constructions that would use this. Like you might want to have some like accounting on chain for your staking pool, and you could actually then provide like validator signatures for this type of thing. I have like a more speculative idea, but you could imagine. So a big thing here is around having like, let's say more decentralized like liquid staking tokens, LSTs. And the issue with this is that if you make an LST, it's like somehow making this token of like validator performance. Cause like right now, there's no way to say like make a token that reflects like staked ETH, right? So, and the reason why you can't really, well, okay, so you can. And the way that people do it is things like Lido, things like Rocket Pool, where you basically have like some other sort of adjudicator that says, okay, this set of validators are like all similar enough in terms of risk profile that they can like sort of underwrite or like back this other token that we make. And, you know, there are concerns with this simply because when you have these like other bodies that are making this sort of claim that like these validators all look enough similarly enough that you can make a single token that is then fungible and represents all of them, you know, there's now centralization concerns, governance concerns, and all of this. So there's like a very much an open research question, like, can we make more decentralized liquid staking tokens in some way? And like one big issue again is that if you just like any validator make a liquid staking token, well, it's not useful unless you have like fungibility, meaning like I kind of want to be able to make a liquid staking token for any validator. And it's hard now because the validators all have different profiles and they look differently and all this stuff. So one thing you can kind of imagine is like, if I could somehow make a proof of validator performance, you could then use that to like vet or like provide some signal into like a liquid staking token on chain. And then you could like maybe then imagine like tranching different levels of risk of these different buckets of validators, and you could do this sort of all trustlessly. The idea here is then that you then need to know how a validator is performing, and then you would get to this use case I called out where you then want to be able to validate signatures of validators on chain, because then you could say, okay, some party submits all these like attestations on chain, and that's where I then need to verify that the validators actually made the right attestations. You could then see, okay, was this attestation timely? Did it attest to the right thing? And, to make a long story short, you start to get some signal of like validator quality, and that would then back into like some sort of liquid staking construction. So there's one thing there. And yeah, I mean, I think there could be like, we could probably sit and think of many more. That's part of the exciting thing with this stuff is like, I want the community to surprise me.
Indeed. And in the presentation, you also mentioned about layer two use cases as well. Projects of rollup can maybe use this proposal. Recently, we had a chat with Ulas, the author of EIP-7212, which is the RIP, Rollup Improvement Proposal. It seems like that is also a precompile for SECP-256R1 curve support. I'm curious to understand here, is this proposal 2537 and 7212, can they be related in any way, maybe supporting, complementing, or kind of contrast in relationship?
Yeah. So they're just different mathematical curves. And so they have different properties. I believe, for example, I was kind of calling out this aggregation capability that we get with pairings from BLS-12-381. I don't think that the R1 curve supports this type of thing. And so, yeah, that's just to give an example that like they're different curves, they have different properties, they're used in different ways in different places. Otherwise, yeah, it's more just because they have different properties, they get used in different ways, and then they just kind of do different things. Otherwise, they aren't really complementary or anything like this.
Right, so they can be used in parallel.
Yep.
Of course. In the presentation, you also mentioned about like present curve that is being used on Ethereum mainnet may have received some kind of complications in the past. So my question is, will this proposal 2537 replace the present curve, or we are going to have it in addition to the existing one?
It'll be an addition. Like, we generally don't want to have breaking changes in Ethereum, which again, I think as time goes on, we see that this is like a very important thing to uphold, but then it also means that if there is a change to the protocol, we'll have it allegedly for all time. So changes should be made very carefully. Like, we'll see what people do. Like in a vacuum, at least I would say you would want to use this curve over the BN curve that's already there. And then, yeah, that does kind of suggest that, like, say in a few years, like if no one's using those precompiles, like it kind of opens the question, could we somehow take them out? It's still a bit tricky because like you still then want to be able to like validate past transactions who might have been using it. So yeah, it's not straightforward to like remove things from the protocol, but it's a conversation you could have.
Yes, of course. I think we would be looking to this conversation maybe after 2, 3 upgrades, not the immediate, because we have too many things lined up there. Very well. I understand this proposal had a lot of benchmarking done in order to make sure that these are good and we are making optimization in gas cost consideration. I wonder if you could maybe talk a little bit more about this gas cost consideration and how they have been addressed. I'm hoping this benchmarking may have helped optimize it.
Yeah, definitely. So yeah, maybe for context, like when we have things that go into the EVM, like you want to then figure out how much they should cost. And we have this abstract notion of gas that like represents a unit of computation. You then want to say, okay, well, we want computation we do in the EVM to like map to actual like hardware that we have today, right? So like if I'm running my solo stake or like my, my validator at home, like it should somewhat be commensurate with like hardware I have on like my home computer. So for that reason, then for any time you want to add a new opcode or like set up precompiles to the EVM, you need to like do this benchmarking process to be like, okay, if we pick like, for example, like 10,000 gas, like that means something in terms of what my hardware or like any validators or, even full node, what their hardware could do, right? And so you want these numbers to like match reality, let's say, in terms of like modern hardware capabilities. And so like, I think even within like the 4 years that we have, there have been like at least two things. Like the first one is, people do have faster CPUs, like better hardware, things like this, maybe more memory. And so that plays into this gas assessment. But also there have been like software improvements. And so over the time, like, so these 4 years, like the BLS implementations, the libraries that implement this curve, like they themselves have gotten better. And there have been new developments around like maybe more sophisticated ways or like more clever ways to like do, for example, like many multiplications at the same time and things like this. And so then you actually then want to have that to funnel back into your gas assessment, because it's like, okay, well, rather than like a naive, okay, if I do n multiplications, it should cost n times, the base cost of multiplication. We can actually then just assume that clients will implement a more optimized thing. And so then what we can do then is that translates to cheaper usage for people using the precompiles. Yeah, so it becomes more efficient, more optimized, and then cheaper to use. So for all these reasons, yeah, I mean, this is something we like regularly want to do. Like we could even claim we should like go reevaluate the gas cost of other things inside the whole EVM. Obviously, then that's consensus change, and so it's like a much bigger conversation to actually go and do that. But yeah, I mean, this is something I think core developers are always thinking about, is like, yeah, kind of accounting for both hardware and software improvements that would then flow back into the actual structure of the EVM itself in the protocol.
Right. And I think at present, there are 10 plus EVM proposals for Pectra upgrade. I hope the suggestion is for future upgrades. Very well. I understand for any proposal, community feedback plays an important role. And because this proposal has been there for about 4 years now, or maybe over 4 years, I'm curious to hear your thoughts on the changes that has been brought into the spec because of these feedback. While skimming through Fellowship of Ethereum Magician page, I came across few additional operations suggestions such as BLS-12 GTADD, BLS-12 GTMUL, so and so forth. My question to you is, are they already included in 2537? If not, is there any plan to include these for Ethereum mainnet on future?
Right. So the ones that you were talking about, they're called like GT, and then like additions and multiplications and like the various flavors of operations you would do. Those are not. So maybe to add some context, like BLS-12-381, so it's like one particular curve, which again is just like we could write down some mathematical equation and we draw a pretty picture in terms of its chart. And this is just like a very well-defined mathematical object. So then in turn, to actually go and use it in these different cryptographic schemes, you need to define structure on top. And the structure concretely, algebraic groups, again, this is just another mathematical concepts, but they are sort of like a subset of the curve that you can use for the primitives you would need to build different cryptographic applications, again, like BLS signatures. And it turns out with BLS-12-381, there's actually like 3 groups that you end up defining. And we call them like G1, G2, and it's called a target group, GT. So this is what the GT means. The idea being is that there's this like pairing operation that we called out. And again, it's like a very special, sophisticated thing. But at a high level, how it works is that you take a point in this first group, G1, another point in this point, G2, and you can feed them into this pairing operation and get back some other point in this target group, GT. So that all being said, for I think what I'll at least say are more speculative cryptographic applications, you'd actually also want to be able to operate over GT, this third group. And so that's what those proposals that you're referring to were calling out, is that with 2537, we have precompiles for G1 and G2 operations, but not GT. And so, yeah, then to answer your question, they are not included in the EIP today. There was some conversation at ETH Magicians and other places around them. And ultimately, I think the inference is that essentially they don't sort of pull their weight in terms of complexity. Kind of like we were talking about a minute ago, when you add things to the protocol, you kind of have to manage them for all time. And so we should do this very carefully. And I don't think there's enough sort of demand or like demonstrated usage for these other sort of GT operations that would justify making the CIP even bigger. That was also another sort of point of initial feedback, is like, not only is this like some new crazy cryptography curve, but also there's like 11 or something precompiles, which is like a lot. Most other EIPs that precompiles only add like 1 or maybe 2. Like honestly, I think literally all the others only add 1 precompile. Or maybe not the other BN. Anyways, point being is like usually there's a very small number. And so this was sort of striking to core developers when they saw this. And there's good reasons to have this many. But again, it just sort of your warning bells go off as a EVM developer, let's say, when you see this. So yeah, for those reasons, like essentially we've decided not to include them. We could always add them later if there's like some new snark scheme tomorrow that's like super cool and like super performant and like very obviously would be useful to have, like they could be added. But yeah, we haven't added them to date.
Sure. So it will be nice to have, but in future, depending upon the demand coming up from the community. Sounds good. Well, Alex, I would like to take your time to maybe collect some feedback. I'll be curious to hear your thoughts on the series, PEEPanEIP. You had done multiple episodes here. We have received quite good feedbacks. But if you could maybe share your thoughts, how we can make it even better for client developers and implementers who are willing to follow this series.
Yeah, I think generally they're super helpful and they're valuable for people. If anything, there's like so many EIPs going through and floating around that it's like hard to keep track of it all. And so, resources like this are really valuable because like I might be a consensus client developer and I might not have time to go keep track of like, for example, all of the latest EOF changes. And so PEEPanEIP, I think, is like a good resource for that. Yeah, keep doing what you're doing. Nothing immediately comes to mind in terms of things we would really need to change.
Thank you. That's awesome. Good to hear that developers love that. And we would definitely continue to do what we do. We'll try to include as many proposals as they are under discussion. It's time to wrap up. And before we let you go, is there anything else that you would like to share with the Ethereum community or people who may be interested in supporting Proposal 2537?
Thank you for having me. If there's any like feedback or questions, there is a ETH Magicians thread that's probably like the best place for community input. And otherwise, super excited that this is in Pectra. And yeah, we'll wait for it to go live.
Of course. Thank you, Alex Stokes, for sharing your insight on EIP-2537. It's been a pleasure having you on the show. And for our listeners, should you have implemented this EIP or want to share any comment, feedback about this, please leave a comment. Be sure to follow Alex on Twitter. And don't forget to like and share this special episode on Ethereum Pectra Upgrade. Subscribe to ETHCatHerders YouTube and podcast to stay updated on the latest development in the Ethereum ecosystem. Till the next time, keep watching, keep listening, and keep sharing your love with Ethereum Cat Herders. Cheers.